So first of all, welcome everybody. Thanks for joining the session. My name is Stephen Donnelly. I'm CTO at Indace. We are a proud sponsor of SharkFest. We do have a room available in Discord, so you can drop by there and find out who we are if you have any questions. And I'll try and be on Discord for some of the conference, but unfortunately time zones make it a little bit difficult. So this talk is, how long is a packet? So how long is a packet? Now, if you ask an engineer how long a packet is, they're likely to give you a typical engineer's answer, which is, well, it depends, doesn't it? So unfortunately, that's not very helpful. And the immediate question is, well, what does it depend on? How would we know how long a packet is? So I'm sorry to shock you with some maths early in the morning in Europe, perhaps, but it won't be too much of it. So before we think about how long is a packet, maybe it makes sense to think how long one bit is, since a bit is the smallest part of a packet, if you like. So the length of a bit is proportional to the rate at which you are sending bits, so how much time a bit takes, and the speed at which a bit travels through a medium. So for example, if we had a bit rate of 1 gigabit per second and we send a single bit and our medium was a piece of fiber optic cable, then the speed that light travels through a fiber optic cable is about 2/3 the speed of light. So about 2 times 10 to the 8 meters per second, 0.67 C. And if you work that out, it turns out that one bit at 1 gigabit per second is about 0.2 meters long. So about 20 centimeters. And that turns out to be about 8 inches, which, if you were paying attention, was the length of distance on our tape measure at the beginning. So that's about 1 bit at 1 gigabit per second in fiber. But if we want to think about a packet, obviously a packet is made up of lots of bits. And if we had, say, let's arbitrarily say 100 byte packet, 800 bits long, that packet is 160 meters long. So we've kind of answered part of the question, which is how long is a packet? This particular packet is 160 meters. And when you think about it, what that really means is if I send that packet through a piece of fiber, which is less than 160 meters long, then the receiver will start to receive the beginning of the packet before I've finished sending the end of the packet. But if the piece of fiber that I have is longer than 160 meters, then there's a point in time at which I've finished writing the bits into the fiber, but the receiver at the other end hasn't actually received any of the bits yet. So that entire packet only exists inside the fiber for that very short period of time. It doesn't take very long, but the packet only exists as a series of bits in the fiber. So the question might be, what happens if we had a really long piece of fiber? How many bits could we actually put in it? Would this perhaps be a useful way of storing data? So I had to think of what would be a long piece of fiber. So I'm based in New Zealand, and I've chosen Auckland, New Zealand to represent where I am. And since SharkFest Europe is in Central European time, I picked Lisbon to represent SharkFest. Lisbon is close to Estoril, where some of the previous SharkFest Europe events have been. And this is a representation of that distance. It's not a straight line through the Earth, but it's a great circle path around the surface of the Earth, which is a little bit hard to see on this map. You can't see both ends at the same time, but we can plot the same thing on a Mercator map, and you can see the path that would be a straight line if you drew it between those two places. And it turns out the distance between New Zealand and Lisbon is about 19,622 kilometers. So my question is, just check it here. Lisbon's not on CEST. Oh, is it too far west? Okay, never mind, pretty close. my question is, if we started sending data into that piece of fiber, somebody laid a piece of fiber directly from here to there, no repeaters or anything in the middle, if we had a strong enough laser, if we started writing bits in, how much data could we put into that piece of fiber before it started coming out at the far end? And we can rearrange our formula a little bit to say how many bits can we fit in a certain distance. And for a gigabit per second, it turns out that you can fit in about 98 million bits of data, 98.1 megabits of data. And sending that data from when the time that I write it in New Zealand to the time that it arrives in Europe is about 98 milliseconds. And that's a one-way delay, which is approximately the same as 12.3 megabytes of data, right, if we convert bits to bytes. Now, I don't know about you, but I think 19,000 kilometers of fiber optic cable is probably less convenient than a USB thumb drive. So it turns out that really long pieces of fiber is probably not a very good way of storing data. But it is, this number that we've come up with is also referred to as a bandwidth delay product. And you can see why. It's the combination of the bandwidth, which is 1 gigabit per second, and the delay, or how long it takes to send the data through the path that we're talking about, the network path, which in this case is just fiber, is about 100 milliseconds. So we've been talking about arbitrary packets so far, but most of the real networking these days on the internet is all TCP/IP. And if you think about TCP/IP, the way that it works is you don't just spray data into a piece of fiber, you send a packet out, and then the receiver sends an acknowledgement back. So if I sent our 100 byte packet from New Zealand to Europe, it takes 98 milliseconds to get there, and then the receiver sent an ACK back, it would take another 98 milliseconds to get to New Zealand. And during that 200 millisecond period, we've
Stephen, I think we lost your voice. We can't hear you.
Hello? How's that? Is the sound back? I apologize for that. I think the headset switched off. Problem with wireless headsets. Where did we hear up to? Previous slide. Okay, so we were just talking about the total amount of a bandwidth delay product, right? So this is the bandwidth, which is 1 gigabit per second, and the delay, which is our 98 milliseconds, which is where we get our 100 megabits from. So with TCP, what you do is you send a packet, the sender sends a packet, and then an acknowledgement comes back from the far end. So if you imagine doing that from New Zealand to Europe, if I sent our 100 byte packet to Europe and then waited for the acknowledgement, it would take 200 milliseconds before I get the acknowledgement back. So during that time, I've only transferred data at about 4 kilobits per second. So as a sender, I want to send more than just one packet before I wait for an acknowledgement to come back. And the way that that's done in TCP is the receiver advertises, tells the sender how much data it's allowed to send before it has to stop and wait for a bit acknowledgement. And the sender has no influence on that whatsoever. It's entirely up to the receiver to say how much data you can send. And the sender has to keep hold of any data in that window, because if it doesn't get an acknowledgement back from the far end, it may have to retransmit it. Or if it gets a negative acknowledgement back, selective acknowledgement back from the far end, it may need to retransmit some smaller part of that. So clearly, if the window is very small, like 100 bytes, over this high bandwidth delay path, then the transfer is going to be very slow and very inefficient. You're wasting a lot of time on the network, lots of dead time in between packets. So how do you know what to set the window size to if you're the receiver? And the rule of thumb is you want your receive window to be about 2 times the bandwidth delay product, which kind of makes sense. So you want the sender to be able to start writing packets into the network and have all of those, write enough packets into the network so that the path towards the receiver is full. And then when the receiver receives the first packet, it sends an acknowledgement back. While the acknowledgement is traveling back to the sender needs to still be transmitting. So it's actually 2 times the bandwidth delay product. And in this case, it would be 24 megabytes. So the TCP window field is only 16 bits wide. It's clearly not big enough. And the TCP negotiation adds a scaling size. So there's a window scaling factor. Advertised through TCP options. It can be as high as 2 to the 14. And when you multiply that out, it means the maximum window that you can advertise without any extensions at least is 1 gigabyte. So for our example, we only need 24 megabytes. If we advertised a window scaling factor of 2 to the 9, we could get 32 megabytes, and that would be fine. So you might be saying, but last time I went to a website on the other side of the world, I didn't reconfigure my TCP stack. I don't remember going in and tuning things and so on. So was I doing things wrong? Is there something that I missed out? And the short answer is probably not. There's a couple of reasons why. One of them is when you are browsing a website on the far side of the world, you're probably not expecting to get 1 gigabit per second of throughput from that website. You're probably only expecting a few megabits per second, in which case your standard window size might be fine. And the other reason is TCP auto-tuning. So most modern operating systems will automatically adjust the buffer size as needed, at least up to a limit. So they don't start with a huge window because that requires a lot of memory to be reserved for each TCP connection, but they can increase it if they need to, up to a certain size. So if that's true, then why did we just bother learning about tuning receive windows? What's the point of that? Well, a couple of things. First of all, not all devices on the internet run modern OSs. There's a lot of IoT devices which might have simpler networking stacks, don't necessarily have the ability to automatically tune their receiver window. And also, if your path happens to be either very high bandwidth or very long physically, like the one we talked about, then the auto-tuning might not scale high enough. So I think Windows will auto-tune up to about 16 megabytes. And Linux, I think by default, tunes up to about 4 megabytes. And both of those values are not high enough to give us our 1 gigabit per second TCP connection between New Zealand and Europe, for example. So what would happen if you had an even longer path, right? What would happen if you had a bandwidth delay path that was really a big number? So this is a diagram to scale of the Earth and the Moon. And the little dot that's moving around represents the speed of light delay between the two. So you can imagine it being a packet, and it's kind of going SYN, SYNAC, ACK, and so on. Play it again. SYN, SYNAC, ACK. And then you get, get 200 OK. So it's going to take a while if you're just transferring messages one packet at a time. Now, the distance between the Earth and the Moon is 384,000 kilometers. It takes 1.2 seconds or more for a signal to propagate in each direction. So what would the bandwidth delay be, and what sort of TCP bandwidth could we get from the Moon? It turns out that there is a laser communications demonstration that was done in 2013, and they beamed data from the moon at 622 megabits back to the Earth. So if we were on the Earth and we were advertising a receive window to that satellite, if we were using TCP and we wanted to have a single TCP connection using all of the 622 megabits of bandwidth, we would need a receive window of 99.6 megabytes. And that's easily within the 1 gigabyte. That's the maximum that can be advertised. So you could actually easily fill that circuit. And if you work out, if I did set my receive window to 1 gigabyte, what's the highest bandwidth I could fit over a single TCP connection from the moon? It's about 3 gigabits per second. And of course, if you wanted more than 3 gigabits, you just open a second TCP connection if you had a high enough speed circuit. So perfectly reasonable. I think that TCP from the moon probably would work, although slow start would be very slow because that initial ramp up of exchange would take quite a long time. So you definitely want to have selective ACK enabled. All right, so if we come back to Earth for a minute, we've been talking about packets as very abstract things so far. How long is a real packet, though, on a real network that we talk about day to day? So we think about an Ethernet frame. If you ask most people what's a small Ethernet frame, they'll say 64 bytes. And if you ask what the maximum Ethernet packet size is, they'll say, well, it's sort of 1500 something, mumble. What the standards say is that the smallest Ethernet frame is 64 bytes and the maximum is 1518. The 1500 byte number comes from the size of the Ethernet payload. But if you work out how many packets can I send of the minimum size on a certain link, the number that you get will be too high if you use 64. So there's something else that happens on the Ethernet link which is not included in this length, which is these extra bits. So before an Ethernet packet is sent on the wire, there's a preamble, which is typically 7 bytes and a starter frame delimiter. And then after the packet, there's an interframe gap. These things can be variable. They can shrink in certain circumstances, but these are the typical values. So what it means is that when we talk about the smallest packet that can be sent on the wire being 64 bytes, on most network links, it's actually occupying 84 bytes worth of bandwidth on the link, of time on the link. And if you work out how many 84 byte packets can I send on a 1 gigabit link, that's where you get that packet maximum packet rate of 1.488 million packets per second. Now this is all well and good, and people really like Ethernet. It's been around for a long time. But people said, you know, Ethernet is really good. What we want to do is we want to run more than one Ethernet over the same physical infrastructure. We want to sort of have virtual Ethernets running on the same network without having to recable things. So they went back to the IETF and said, hey, how can we do that? And
Stephen, we lost your audio again.
we're back. Sorry about that. I think the headset has some issues. I'll try plugging it in. Okay. So people wanted to run virtual networks, and the IETF said, okay, that's all right. What we'll have to do though is we'll have to make the packets larger, because if we don't do that, then if I send a 1500 byte packet onto a network that has VLAN tags on it, it wouldn't fit. So they extended the maximum length by an extra 4 bytes to fit in this VLAN tag, and we get 1522. The difference between the packet length and the length on the wire is still 20. So that 20 byte number is a good one to understand. The minimum size packet is still 64 though, that's unchanged. So the Ethernet payload can be as low as 0 bytes, and it will be padded out with zeros. So the minimum amount of padding that you can get here is 42 bytes rather than 46. So that's where that number comes from. Now, this is all well and good, and people really liked VLANs, and they said, hey, this is really good. And then telcos said, well, VLANs are really good, and we like using them for setting up connections to multiple customers over our networks, but our customers also want to use VLANs. So what we'd like to do is we'd like to run VLANs on top of other VLANs. So our customers can have their VLANs, and then the carriers can also have VLANs. And the IETF said, look, you guys have got to make up your minds, stop asking for more bytes. And they decided that they weren't going to just add another 4 byte VLAN header. Instead, they came up with this idea called envelope frames. So what they said is, we're not going to keep changing the length of the Ethernet packet because it's too confusing for everybody. What we'll do is we'll define this variable length envelope, which is anywhere between 0 and 482 bytes. And you can put whatever you like in there. You can have multiple VLAN tags. You can also use it for MAC security. So if you want to have a secure layer 2 network, you can do encryption at the Ethernet layer. You can use this envelope header to put MAC security in. And that extends the size of a frame then all the way up to 2000 bytes. So the length of the packet from the beginning of the MAC header to the end of the checksum is 2000 bytes. And if you include the preamble and the interframe gap, we're up to 2020. So you can finally answer the question now. When somebody says, what's the largest Ethernet packet you can have? It's 2000 bytes or 2020 if you're including those extra bits. But you might be thinking, hang on, I'm pretty sure I've heard of packets that are bigger than 2000 bytes. What about jumbo packets? Well, jumbo packets, anything over 2000 bytes are not IEEE Ethernet compliant packets. They are non-standard or vendor extensions, and they can potentially cause interoperability problems. The reason being that there's no way for an Ethernet device to signal back to a sender that the packet that it sent was too long. The only thing that it can do with the Ethernet packet that's too big is drop it. It can't fragment it or forward it in any way. The second reason that the IEEE were not keen on extending the length of a packet is to do with the Ethernet checksum. So the Ethernet checksum is a 32-bit field, which provides a check against corruption of the data in transmit and transfer. Now, the problem with a fixed size checksum is that as the packet gets bigger, the checksum stays the same size. So its protection is essentially being diluted over a larger packet. And for packets larger than 2000 bytes, the probability of you getting a false positive is higher and higher. So that is, with a very large packet, I could have a bit error where the resulting checksum is the same as the good checksum, so what the checksum should have been, which means that I get an error that's transmitted by the network that I can't detect. So in order to deal with, in order to provide effective protection against corruption on the network, the IETF wanted to limit the size of packets and not make them too big. Okay, so this is SharkFest, and you'll want to see the inevitable Wireshark live demo. So let's have a little bit of a look at how Wireshark reports about packet length, what it tells us about it, and see if there's anything there. So grab my Wireshark and open up one of these trace files. Hopefully that's big enough. Yeah, I can still see the chat, good. All right, so now this is not a very exciting trace file, so I haven't bothered sharing it. This is just something you can collect yourself and have a quick look at. And we can see, just looking at the default display, that there's a column for length, which tells us the packet length here, 60 bytes here. And if you look in the dissection view under the frame section, this is all information in square brackets. So this is all information which Wireshark has computed about the packet or has been told about the packet. It's not data that was present on the actual wire. And you can see in the very top line, it immediately says the packet was 60 bytes on the wire, 480 bits long, and we captured all 60 bytes of it, 480 bits. And if we want to find out what's the smallest packet, for example, that we have in this packet trace, you can just click on the column heading and sort by it. So let's sort by packet length. Let's scroll up to the top, make sure we're at the top. And here we go. So here's an ARP packet, 42 bytes long and 366 bits on the wire. Now, that seems like a problem because we just went through the length of packets and we just said that the smallest packet that you can get on Ethernet is 64 bytes. So what's going on? If we have a look at the frame, look at the next layer down, it is an Ethernet packet and it's an ARP packet. And the packet just cuts off at the end of the ARP layer. So if you click on the ARP to highlight it, you can see it stops there. So what's happening is an ARP packet is short enough that it requires some padding to reach the 64 byte length. And Wireshark is not showing us that. And the reason for that is that Wireshark can only tell you about what it receives. So Wireshark is getting its packet from the libpcap library, and the libpcap library is reporting the length of the packet that it saw and how many bytes were captured. libpcap gets the packet from the operating system. The operating system gets the packet from the device driver, and the device driver gets it from the network hardware. So somewhere in that stack, probably in the hardware, the device said, this is an ARP packet, it's quite short, and there's only padding and a checksum at the end. It'll check the checksum to see that it's valid, but then it won't bother actually giving you the checksum. If the checksum is bad, it'll drop the packet. You'll never see it in the packet capture. So that's why this frame is short. So even though Wireshark is saying that it's 42 bytes for this ARP packet, it is actually 64. And if we look for the longest packet in the trace, click on the length again to sort by reverse, scroll up to the top, we get 1514. So again, 1514 is 4 bytes short of that 1518 value. And that tells us that there is no checksum at the end of the packet. Yeah, it's a bit hard to scroll down. Okay. So what would happen if you had a packet capture system where it gives you all of the bytes of the packet, not just cutting it off if it happens to be extraneous data that's not very interesting. So here's an example of a trace file that was captured on a device that does capture the whole packet, including the padding and the checksum. So if we have a look at this, we can see sort by shortest and scroll to the top. The shortest frame is once again an ARP packet, but this time its length is being reported as 64 bytes. And if we open up the Ethernet frame, we can see the destination and source address and the ARP type, but this time we can see the padding as well. So that's the padding between the end of the ARP frame and the end of the Ethernet packet. And then we can see the actual Ethernet checksum value itself. And Wireshark has even checked it for us and told us that the checksum here is valid. So that's the difference between a packet capture device that includes the full packet, including the checksum, versus one that doesn't. So it's actually the same traffic, the same packet type, but it is being reported differently. Okay, so what else can happen when you're doing packet captures with Wireshark? So here's another interesting one. So if you have a look at this trace file, the first thing we notice is we have a packet here that's 2,962 bytes long, the very first packet in the trace file, which seems a bit odd. Again, we just went through, 2,000 bytes is supposedly the maximum. So what is the largest packet that we've got in this trace file? I'll click twice to sort by largest, scroll to the top. we've got a packet here which is 23,234 bytes long, which again is much bigger than 2000, and it's even bigger than 9000. So what's going on here? Is this packet really that big? So let's have a look at the IP header. So the IP header has a total length field in it, and the total length field agrees with it. So it says this is a 23,220 byte IP packet. And it's TCP frame. So if you look at the TCP header, Wireshark has calculated the TCP segment length has also been 23,000 bytes long. So Wireshark really thinks this is a very large packet. Of course it isn't, because Ethernet doesn't support packets that large, and this was captured on a real Ethernet network. So what's happening here is the networking device has segmentation offload accelerations turned on. So rather than receiving packets one at a time and passing them up to the operating system, it's able to recognize that packets in a sequence are part of the same flow, and it will aggregate them together into a single larger packet, updating the IP header and updating the TCP sequence number information to turn a number of smaller packets into one super packet and send it to the operating system. The reason it does that is to reduce the rate at which the operating system has to process packets. So reducing the event rate, the packet rate, reduces the CPU load on the system and makes it more efficient and able to transfer data faster. So if you do see that value, if you do see large packets like that, you'll often also see that checksums in the packets are not calculated correctly. That's often the case on transmit packets, where the network adapter is offloading that work, so it's doing it for you. There's two things you could do here. One of them is you can go into your network card configuration and you can turn off these offloads, often called GRO, LRO, those kinds of things. However, if you're trying to debug a networking issue and you do that, then you're changing the behavior of the machine that you're trying to understand, right? So you might be better off to use a network tap and then receive the packets on a system other than the one that you're trying to debug at the time. Okay, and I've got one more trace file here. It's an interesting one. So let's have a look at these packets. We'll see if we can find the smallest one. So here's a small packet. So this one is an ARP packet, but this time, rather than being 42 bytes long or being 64 bytes long, it now says the ARP packet is 80 bytes long. And if we have a look at the packet, we see the fourth header down here is an exablaze trailer. And what this means is this particular trace file is captured on the output of a packet broker. So a network packet broker is a device which captures all packets on multiple physical ports, timestamps them, and then sends them out to one or more analysis systems. These devices frequently add a trailer on the end, or sometimes a header on the beginning, with extra information. In this particular format, Wireshark has a dissector for it, so we can open it up. It recognizes it as an exablaze trailer. It tells us which exablaze device it was passed through, so device 0 in this case, which port it was, and what the timestamp for the packet was. Highlight that in the frame. So we've got the ARP packet, and we've got the padding at the end of the original packet. And then we've got the FCS from the original packet before it hit the packet broker. And then the packet broker has added its device ID, the port, the timestamp, and then the checksum for the new packet is after that. You can see though that the if we highlight the exablaze trailer, the checksum, Ethernet checksum is not considered to be part of that. So what we can do is go up to the Ethernet protocol stack, go to protocol preferences, and tell it just to assume that packets have a checksum on the end. If we do that, and we open our Ethernet layer, now we can see that it's found the checksum for the outer packet, the one that the packet broker presented, and it's able to check that it's correct. So that's a useful thing to be able to do. Back off. Now, I just want to note that packet brokers are very useful devices. This is not a criticism of a packet broker. That information wouldn't be available otherwise. So it's a very useful thing to be able to do. This trace file was provided by Exablaze. Endace doesn't make packet brokers, but we are partners with some companies who do, and they're very useful things. Okay, so I'll jump back to presentation. So these slides are just a quick recap of the things that we discovered while looking through a few different trace files. So I won't go over them in detail too much. We talked about how Wireshark displays the packet length. We talked a bit about some of the network card accelerations and why they are there. We talked about pseudo headers, so packet brokers can add pseudo headers or trailers. Sometimes Wireshark has dissectors for them. Sometimes they're automatic. Sometimes they have to be turned on manually. So it really helps to know what the context is of the packet traces that you're looking at. All right, so let's think about speed for a minute. We've seen that the same packet in Wireshark can be reported anywhere from 42 bytes up to 80 bytes in length. Is that something that we should be concerned about or not? So if you think about speed and how we talk about that, for a particular point in a network link, at any one time, either a packet is there or a packet isn't. So it's very binary. The network is either 100% utilized or not utilized at all at that instant in time. So when we think about speed in terms of networks, what we're really talking about is throughput, which is over a certain period of time, how many bytes of data are actually transferred. And we typically normalize that to bits per second, so 1 gigabit per second link. Bandwidth is a maximum link throughput, so that's a 1 gigabit per second. And goodput is kind of the achieved transfer rate. So if I'm doing a TCP connection between New Zealand and Europe, then the size of the file that I download divided by the total amount of time that it took would be the goodput. So when we're trying to work out the throughput, we need to be careful about how we count bytes. First of all, you should always use the length value, not the cap length, because if you're truncating packets in the capture system, you'll underestimate the throughput that you're seeing. Whereas length always refers to the length of the packet on the wire, at least, as well as the PCAP was able to determine. So that depends on your capture system. If your system doesn't capture the checksum and the padding, then you're going to underestimate the throughput and the link utilization. So you might think that it's only doing 800 megabits, but it's actually consuming 1 gigabit of bandwidth, for example. If you're including pseudo headers and trailers, we noticed that Wireshark was reporting the length of that ARP frame as 80 bytes. So if you multiplied that by the number of packets, you would end up with a bandwidth that's higher than was actually on the original link. But it is the bandwidth that was available, that was present on the link between the packet broker and the capture device. And if you're capturing from a network card device that has some offloads enabled, not only are you potentially underestimating the throughput and utilization because it's bundling multiple packets together, but your packet counts may and packet rates may be wrong as well. So if you're seeing a discrepancy between the number of packets received by your device, say TCP dump, versus what the switch is telling you, it could be because frames are being consolidated together. If you're considering if you're considering a provisioning exercise, so how much bandwidth do I need to provision between some sites, then you do need to consider that as well as throughput, because that includes the preamble and the end-of-frame gap times. Real networks have a mix of different packet sizes. If the network use cases are mostly bulk file transfers, then the bandwidth and the utilization will be pretty close, whereas with small packets, you get that multiplying effect. So it might look like you're only using 500 megabits, but because the frames are short, the overhead, that Ethernet tax that you're paying is higher, and you're actually utilizing more of the link than you think you are. So Another place where packet sizes become quite critical is when things start breaking. So MTU mismatches, that's what happens when we have disagreement about what size packets we're going to accept. So what's an MTU? The MTU is the maximum transmission unit. And every link will have an MTU defined, at least in IP networks, and that's the maximum size packet that will be accepted for reception on a link. We tend to think we live in an Ethernet world, but not everything is Ethernet, and different links may have different MTUs. Some people may turn on jumbo packets. And we also often see MTU variations around encapsulation. So things like tunnels, VPNs, virtualization, mobile IP, all of those kinds of things. And the reason this is a problem is that an Ethernet switch can only drop frames that are too large. So if I'm an Ethernet device and my MTU is 1500 and I receive a packet that's larger than that, there's no way for me to do anything about it except drop it. Whereas an IP router can be a bit smarter. So if it's an IPv4 packet, IPv4 network link, packets can be fragmented mid-path. So a packet is traveling from router to router down a network path, and then the next link has a lower MTU. The router can choose to fragment the packet into pieces that are small enough to fit into the next network link. It's up to the receiver to reassemble the fragments back together to get the original packet. And that is completely transparent to the sender. The sender doesn't know that a router partway through the network has done that. However, this is usually considered inefficient. It loads up the CPUs on the routers, and it also has a higher resource requirement on the receiver, so it has to reassemble the fragments. And the individual fragments can be lost or can get out of order. So if a fragment is lost, then the sender will not get an acknowledgement for it, and the sender will have to resend the entire original packet again. The packet will hit the same router and get refragmented again, and so on. So it's quite inefficient. To prevent that inefficiency, IPv4 has a don't fragment bit. So the sender can say, when sending this packet, please don't fragment it. And then what the router should do is, if it needs to fragment it and it can't, it sends an ICMP message back to the sender saying, fragmentation was needed, but you set the don't fragment bit, so I couldn't forward the packet on. And end devices use that for path MTU discovery. So if I get a message back saying the packet was too big, I can try sending it again with a smaller size with don't fragment set and see if it gets through this time. That way I can find out over an entire path what is the MTU value that will work end to end. What about IPv6? So IPv6 doesn't support fragmentation in the mid-path. So if I'm an IPv6 router, I don't have to worry about fragmentation because it's not something I have to do. If the packet that I've received is too big for the next link that I need to forward the packet onto, then I simply send an ICMP v6 packet too big message back to the sender, and they have to do path MTU discovery. But what if it's not possible to make the message smaller? So if I'm sending a UDP frame, a UDP packet is a single datagram. It's a single message. You can't just treat it as a stream of bytes. So how do you do that over IPv6? IPv6 has an extension header for fragments, but it's end-to-end fragmentation. The sender explicitly fragments the packet before sending it out onto the network, and then the receiver reassembles those fragments and delivers the too large packet to the application at the far end. So a few minutes left. This is an example of a connectivity problem. So this is a little example from the early days of the internet. I'm at home, I'm connecting to my bank's website, and I can browse their website fine, there's no problems. Then I go to log into their secure encrypted, banking login system. And as soon as I try and do that, the connection basically hangs, and nothing else happens after that. And some of you looking at this can already spot one of the problems. The connection between the house and the ISP is ADSL rather than Ethernet. So if we put the MTUs of the links on, ADSL in this case was implemented as PPP over Ethernet. so IP over PPP over Ethernet, there's an 8-byte PPP header in there. So the MTU of this link is slightly lower than the MTUs of all these other ones. Now, when I was browsing the website, this was working fine. But when I went to log into the secure site, it didn't work. What's going on? Well, if we imagine the end device here is connected to its local Ethernet, so its MTU is 1500. It can send a 1500 byte packet out. It'll get to the router. The router will say, the MTU is too small, I'll have to fragment it. So it can fragment those packets. The fragments will get transferred all the way to the bank, and then the bank will acknowledge them, and that's fine. So what was happening when I went to log into the secure site? Probably this. The firewall at the bank was incorrectly configured to block ICMP. So I go to log into the secure site. The GET request goes down, no problems at all. And when the bank wants to send a 1500 byte packet back, it sends a large response back. So it sends a 1500 byte packet with its MTU, travels all the way down to the ISP. The ISP says, I need to fragment this packet, but it has don't fragment set on it. So I will send an ICMP message back to the bank that they need to reduce the size of their packets. But if the firewall drops it, then the bank doesn't know that that packet couldn't be delivered, and away you go. So why would they set don't fragment? Because it was SSL, and SSL typically has don't fragment set. So the short answer there is don't block ICMP unreachable messages. That's going to prevent you from being able to do path MTU discovery, and that may prevent you from being able to connect to certain sites. There is another workaround, which is the router at this end can pin the MSS advertisement. So when this machine sends its packet out, it advertises that it can receive 1500 byte packets, and that goes right down to the far end. But what can happen is this router can reduce that advertised size for the MSS down to the link that it knows about. That way the bank won't try sending a 1500 byte packet down this link. So just to recap, we talked a bit about physical packet lengths, about bandwidth delay products, what the IEEE call long fat networks. We talked a bit about Ethernet frame lengths and how Wireshark captures packets through libpcap and some of the unusual things that you can see in trace files, how throughput's calculated, and what happens with fragmentation and path MTU discovery. So thank you for attending. Please fill in the survey. Let me know if you learned something, if it was valuable. Let me know if I got something wrong other than confusing IETF and IEEE constantly. And also let me know if there's anything you think could be added to this presentation. So is there anything else that if you were giving it that you would talk about? And I think we've got a few minutes for questions. Have a look at the chat here. Thanks, Jeff. There's a QA thing here. Thank you. And I think when the session closes, you'll be automatically redirected to the survey. So you can fill that survey in and just let us know what you're thinking. Few minutes left. If you do think of anything or you'd like to have a chat, I will be on Discord, either in the in-days room or in one of the sessions. So please do swing by and say hello.